Divergence and curl. This definition says if F equals PQR is a vector field in R3 and PXQY and RZ all exist, then the divergence of S is defined by the div of F equals PXQY plus RZ. And another way to write that is dP over dx plus dq over dy plus dr over dz. Take a look at this note here. The note says the divergence of a vector field is not a vector field, but a scalar function. In terms of the gradient operator, sometimes they call this the del operator, and that equals d dx, d dy, d dz. Divergence can be written symbolically as the dot product. The div of f equals del dot f. So when I see those together, I should think of that. Now think about what this is saying here. So if I have that del operator, and I'm just going to write it down here, and I take and dot that with f, which is p, q, r, then I'm going to get d dx p, d dy q, and d dz r, which is actually what we see here, or what we see here. So again, it's all the same, and they just told us another way we can actually think of div of f as del dot f. Now what the div of s tells us, so let's assume we have this surface here, and then we have this vector field on this surface. At any given point, the div of f is going to tell us how much at any given point is the vector field pushing outward. So the book uses this idea of elastic band. And is it going to crunch in and get smaller area, or is it going to get larger? And if it gets larger, that means there's more pushing out all the way around it. So if the area increases, that's what's happening. And that div of f would be a positive. Now if it's starting getting to get smaller like this, that means more is pushing in. So that means if it's pushing inward, then that would be a negative div of f. Or if it stays constant where it doesn't increase or decrease, then we would say the div of f is 0. So that's an idea of what we're really dealing with here when we talk about the div of f. So when we talk about flux, the div of f is going to be a component of calculating that component, the outward flux. So if it's outward, it's going to be increasing. So let's take a look at number 223 now. It says, for the following exercises, find the divergence of f. So here's my p, here's my q, and here's my r. So I got to do px. So that's going to be 3yz squared. So I'll just write div of f first. Okay, so that's going to be 3yz squared plus, and that's with respect to y, so 2y sine of z plus, and then that's with respect to z, so 2x e to the 2z. So this would be my div of f for number 223. So now let's take a look at 224. 224 is a two-dimensional divergence of f, or div of f. And this is my p, this is my q. So if you look below here, look at the div of f down here, and it's down at the bottom here. It says, note, this is merely helpful notation because the dot product of a vector of the operator and a vector of the function is not meaningful to find given our current definition of dot product. So it says if f equals pq is a vector field in R2 and px and qx both exist, then the divergence of f is defined similarly as px plus qy. So it really doesn't change what I do here. So this is just going to be the derivative of sine of x with respect to x. So that's going to be cos of x plus cos of y. So that's going to be the derivative of that is going to be negative sine of y. So that's going to be my div of f for 224. So it's just that simple. I just take partial derivatives and add them because it honestly is just a dot product. And again, like I said before, we're going to use this for outward flux. So there's our answers.